Hello everyone, this is a rerun of the webinar that we held earlier today. It seems like the video unfortunately did not come through entirely clearly on that one. I apologize for that. So we're going to go through the presentation again and record it at full resolution. I'm going to take a bit longer to go through everything in this video because you can easily skip ahead or skip through if you want to. And the project files are available for download via the link in the description. Or alternatively, you can please contact me via our website www.dizzy.co.za and I'll send them to you. So the agenda for our presentation is that we're going to do a walkthrough in Proteus of some basic schematic capture, some basic PCB design including length matching, some 3D visualization including exports of the 3D in step formats or otherwise, go over file output of course, and then some microcontroller simulation and code debugging including USB simulation and debugging, some differential-pair routing, some high-speed design features there, and then some report generation, and the questions and answers we're obviously not going to do in a recording as opposed to a live webinar. The project that we're going to do, it's a simple project. We just want to get through the features quickly without spending too much time. It's called AN to PWM. What we're going to do is we're going to read an analog signal. We're going to convert that analog signal into a PWM output. We're going to scale the duty cycle of the PWM according to the level of the analog reading. And we're going to set 3 LEDs depending on the reading level, low, OK, or high. And we're going to write the reading out on UART every 500 milliseconds as well as on the USB every 500 milliseconds. The project code is pre-supplied. We're not going to spend time writing the code during the presentation. This is a quick preview of the schematic that we're going to design. Not anything too big, and that's the PCB that we'll design again. Very small project. We just want to get through the features as quickly as possible. And that's a preview of the microcontroller simulation and code debugging that we're going to do. And finally, that's a quick preview of the differential-pair routing that we will eventually do. So this is the home page that we're going to see when we start Proteus. The first thing we're going to want to do is to start a new project. We're going to call this AN to PWM. We're going to place it in our projects folder. We'll use the default schematic, default PCB. We're going to start off with a 2-layer board for now, just to keep things simple. If we wanted to create a 4-layer or more layers board, we'd click the stack up wizard, choose the number of layers that we wanted, set our core and prepreg thicknesses as well as the dielectrics if we wanted to. We could also create power planes on our layers if we wanted to. And we can change layers to be a plain layer or a signal layer. Plain layers not allowing any signal tracks on them. This is again a high-speed design feature. On the next track, on the next page, we would be able to set up our drill pairs, our vias for blind and buried vias if we had a multi-layer board. Once again, we'll we'll get to that later when we switch to a multi-layer board. The next page offers us a preview of the board. It's currently just a 2-layer board, so there's not much to see. There's only one through-hole via, no blind or buried via possibilities. We're not going to create a firmware project. I've done the firmware for our project in MPLAB X as well as in Micro C. We can use Proteus as the IDE for developing our project if we want to, but we don't have to. If we can use any IDE we like, as long as we get a hex file or a COF file at the end of the day, we can bring it into Proteus and simulate it. If we wanted to create a flowchart project, that would be the option we would select. That would be using the Visual Designer module, where we can use flowchart blocks to develop our code. And that's it. You can hit finish. Okay, so this is the Proteus window layout. We have our main editing area on the right and our tool nodes on the left. And the first thing we're going to want to do is pick the devices which we want to use in our project. So we can get a pick 18F, 27J53. Using a pick microcontroller here, but we could use any other microcontroller we like. You could use the AVR or an ARM microcontroller. We're just going to use a pick in this project. Okay, the next thing I'm going to pick is a generic resistor. We could pick specific values of resistors, 10K, 1K, 470 ohm. I like to use a generic resistor and then just assign the values that I want to it. We're also going to need a electrolytic capacitor. Again, I'm just using a generic device there. We're going to need some red LEDs, and we are going to need some green LEDs. So okay, next we want a micro USB connector. So we're going to use this Molex part here, 473460001. This part has already been brought in from the online libraries. Proteus is integrated with the online library of over 15 million parts, provided by Schematic. If I wanted to search that online library, all I'll do is click this button here at the bottom, and then I can see there's a lot of other components available as well. Proteus also has the ability to import from a number of other online sources: Ultra Librarian, Snap EDA, PCB Library Experts, DigiKey, RS Components. You'll just do that via the library import part dialog. Okay, the second last part we need is a shrouded header. So this part again I've already imported from the online library, and this is something that I would have looked up on DigiKey or RS Components and something like that. Found the part I wanted and then searched for it in here via the part number or otherwise. And finally, we just need a little 5-pin header for our in-circuit serial programming for the microcontroller. And that's it. That's all the parts we needed. We can start placing things down and wiring them up. So let's put down our PIC 18F27, J53. We're going to hook up the master clear. Hook this up to power. we're going to pull it high so that the processor isn't continuing reset, obviously. These power terminals, if we don't give them a specific name, they're going to default to VCC VDD. You'll notice that the microcontroller, the VCC and VSS pins are missing, and that's because they've been hidden when the microcontroller was designed. If I want to get to them, I can go to the Edit Component dialog, click on Hidden Pins, and I could change the nets that these are connected to here if I wanted to. The nets are set up under the Configure PowerL dialog, the power net. You can see here our VCC VDD net is currently set to 5 volts. I'm going to set that to 3.3 volts. This doesn't really matter for PCB design purposes. It's more relevant for simulation purposes. Okay, we're going to hook up the VUSB to power as well. Okay, and then our electrolytic capacitor. We're going to change the value on our electrolytic capacitor to 10 UF, and we're going to get a SMD package for it. Surface mount package as opposed to the 3 volt package which it was defaulted to. Okay, so that's fine. Next thing we're going to do is place our shrouded header for our power input output and for our analog in and PWM out. So I'm going to use some terminals to hook this up to the microcontroller. I could draw a line down and connect it straight to the microcontroller, but I'm going to use some terminals because it looks a little neater and also because it will make things easier when we get to the schematic stage. Sorry, to the simulation stage. Okay, I'm just going to copy these across to my microcontroller. Okay, let's place our 3 LEDs. Need a current limiting resistor for our LED, of course. Again, I'm going to use terminals to hook these up. And I'm just going to copy this LED 3 times. 2 copies rather. Okay, and hook the other side down to ground. Okay, we need to replace the middle LED with the green LED. So just click on top of it, ask me do I want to replace it. Yes. It's now being replaced with the green LED. And we need to label these guys. Okay, we also need to wire these guys up to the microcontroller. Okay, and this time I'm just going to select the labels from the drop down. I'm not going to type them over again. This can also just help to avoid typos in naming your terminals. Okay, we need some programming connections for our microcontroller. We'll call these pick program clock and pick program data. Okay, we need to quickly add the ICSP header. Okay, this is going to be the master clear. This one should be the program data. And this one here should be the program clock. Okay, and we just need to add a connection to the actual master clear pin. Okay, and I'm going to add a little note to this guy here that this pinout is a picket connector pinout. He's added that text to my schematic there, my note. We need the USB connector. So we're not going to worry about the V bus pin, we don't need it for this design, nor the ID pin. This is going to be USB data minus. This is going to be USB data plus. Right, and we need to hook obviously the ground up. That's it. We need to add these terminals to our microcontroller. Okay, and that's pretty much it for our schematic design. We need to do a little bit of prep before we go to the PCB layout. We're going to change the package on our microcontroller from a through-hole DIP28 to an SOIC. We're going to change the package on our resistors also from a through-hole to an 0603 surface mount package. Okay, and then we want to copy that 0603 package easily over to the rest of the packages. So I'm going to do that using the Design Explorer. I'm going to filter two resistors, and then I'll just copy that guy across to the rest of them. I also want to give my LED resistors a value of 1K, otherwise my LEDs are not going to shine very brightly. I'll just copy that across as well. I can also see that my LEDs are currently missing packages, so I'll just go and get a package for them quickly. I'll just use the LED package. Okay, copy that across as well. Okay, and that's it. We're ready to move on to the PCB layout. The first thing I'm going to want to do is draw a board edge for my board. So I'll select the board edge layer. I'm going to make this approximately 40 by 47.5. There we go. Now we could use the auto placer to place our components, but this is such a small board, it's going to probably actually be easy enough to just place them manually. So I'll place the microcontroller right about in the middle of the board. I'll put down my 3 connectors next. My in-circuit serial programming header. Oops, I have selected package mode rather than component mode. So I've just been placing packages rather than components. Components are parts which come through from the schematic. They have a part reference. Packages are used by the components, but they're not linked to the schematic. So what I actually want here is the components. That looks better. I can see some rat's nest lines now, as well as the part reference. Okay, my shrouded header. Okay, we don't want that label hanging off the edge of the board, so we'll just bring it down there. And our USB connector. Again, we don't want the label hanging off the edge of the board, so we'll just move it over there. Okay, so the green lines we're seeing here, these are called rat's nest lines. They basically show you what needs to be connected to what. The yellow lines are called force vectors, and they tell us approximately where this component wants to be in order to minimize the length of the rat's nest lines. You're very rarely going to place a component exactly where the force vector is pointing to, but it is nonetheless a useful indicator. If I wanted to turn the rat's nest and the force vector lines on or off, that can be done from the display settings dialog. And leave them on for now. Now we notice that our micro USB connector has a number of red circles around it. These are DRC errors, and the DRC error is that the clearance between these pads is a bit closer than what our DRC is currently set for. So we're going to change our DRC to tolerate some smaller distances. Our PCB manufacturer is capable of handling these requirements, and all of our DRC errors are now cleared. We do have 14 missing connections because we haven't started wiring anything up yet. I just wanted to show you something regarding the rat's nest lines. If I were to start routing a track, it's going to only show me the rat's nest lines for that particular track. It's a nice little feature. Another way that we could have resolved the DRC errors around the micro USB connector, if we didn't want to change the DRC settings for the whole board, we could have placed a DRC room around that component specifically and changed the DRC rules in just that area. Right, so let's place our LEDs quickly. Okay, and the resistors for our LEDs. Okay, and our pull-up for our master clear on the microcontroller, as well as our core capacitor. Okay, that's it. All our components are placed. We want to add a little text to this board just to explain what some of the things are. Put it on the top sort there. So this LED here is the low LED. This one here is the K LED. And this one here is the high LED. And we also just want to add a board name and revision. Okay, and a pin 1 marker for our in-circuit serial programming header. Okay, and let's pretty up our font a little bit. We're going to change the font here to Arial. Okay, that looks a little prettier. Okay, and let's go ahead and hit the auto router. Okay, that's great. The auto router has done a pretty good job here. If I wanted to change something, for example, instead of routing this track through the middle of this resistor, let's go and just take it underneath. There we go, that's how I can do that. I can move tracks around if I want, so on and so forth. And it's very, very easy to do, very intuitive interface. Okay, we're going to add 2 ground planes to the board, top and bottom. Okay, so I'm going to hook it up to ground on the bottom copper. Hook that up to ground on the top copper. I'm just going to briefly demonstrate the length matching feature. If we wanted to match the lengths of these 2 tracks, I'll just highlight them and then say match root lengths. It's going to add a little serpentine squiggle there for me. I can move it around if I want to. And length matching, again, high-speed design feature. And we'll chat about that a little bit more when we get to differential pair. Length match these USB lines as well. So we don't need to length match these lines, but it provides a little bit of opportunity to just demonstrate the feature quickly without getting into a heavy high-speed design board. Let's take a quick look at the 3D visualization. Okay, so that looks pretty good. Our shrouded header hasn't come through entirely correctly in the online library. And our LEDs are currently all blue. Whether or not that bothers you is up to you. But we'll go ahead and fix both of those issues. So if we go back to the PCB layout here and we go to the 3D models of the shrouded header, we can just change these offsets a little to fix this up. Okay, it's looking a lot better. Okay, and now for our LEDs. So in order to give these LEDs different colors, because we have 2 different colors here, green and red, they're currently all assigned to the same package, which is the LED package. I'm going to need to create 2 two different packages for them, so that we can give them different properties. So I've gone to my package mode again here now, the same thing I did earlier by accident, and placed a blank version of the package, and I'm going to use that as a basis to make some new packages. So I'll make a package here called LED-red. Okay. And now I have a red LED here. Okay, and I'll do the same for my green LED. Okay, that looks good. And I'm just going to go and change the properties of these guys to use those new packages. Okay, and that's now looking entirely correct. I can turn the components on or off if I want to. This can sometimes be nice for checking if you have things like custom solder paste and stuff like that. Then this can be a nice way to check that the paste is exactly where you want it to be. There is also a feature in the PCB layout where we can say draw full solder resist as well as full solder paste, and then we can see exactly where those are. Here they're kind of following the components pads, so there's not really a lot to see, but if you were doing something slightly more unusual, then that would be a good way to check it. On the 3D visualizer, the colors are not really distinct enough right now to see the difference really clearly. So let's change the paste to be a really bright color, and there I can clearly see where the paste is going to be on my board. Let me just change it back to something more sensible. Okay, if we wanted to output a 3D MCAD file, like a step file of the board, then we can just go to the output menu and select generate 3D MCAD file. Hit generate, and that will output the file for us. Gerber files are also generated from the output menu. Do we want to run the pre-production check? Yes. Okay, it just checks for any problems with the board. No problems that to be found. Okay, and we just hit OK, and it's going to generate our CAM files for us in the directory that was specified in the dialog. Our pick and place output for automated assembly is also available from the output menu. This is fully customizable. And our bill of materials is available in the bill of materials tab. This is also again fully customizable. It's a HTML file. You can also output a spreadsheet and PDF if you want to. Okay, and then the last one I want to mention is the assembly plot file. It's going to again be useful for handing over to the guys doing the actual PCB assembly. And it's just a nice picture of the board with the components clearly labeled, exactly where they are. Okay, let's move on to the simulation. So we're going to add a few extra components to assist with the simulation. I'm going to put them at the bottom left. They don't have to be there, they can be anywhere in the design, they can be on a separate sheet. And I'm also going to draw a little box around them just to make things neat. But again, the box doesn't actually do anything, it's just there for my to make things look neat. It doesn't affect things anyway. Okay, we are going to go and get some virtual instruments, an oscilloscope, a virtual terminal. We're going to go and pick a potentiometer to help us generate our analog input, simulate our analog input. And we can go and plot this down. And just move these labels a little out the way. Oh, we need a bit more space here. There we go. Okay, so we can hook this up to the analog input pin on our microcontroller. I also just want to add a voltmeter here so that we can get a visual display of our reading during the simulation. And we also need to hook up our oscilloscope to the PWM output. And we want to hook up our virtual terminal. This is a UART terminal. We're going to hook this up to the UART pins of the PIC. Okay, we need to add the pins to the PIC as well, to the microcontroller. Okay, that's the PIC TX, and that's the PIC RX. Okay, we want to tell Proteus that this potentiometer is only for simulation purposes. We're not going to use it on the PCB layout, so we're just going to go and take exclude from PCB layout. Similarly, we need to tell Proteus that we don't want to simulate these connectors. Proteus doesn't know what we intend to plug in there, so it doesn't know how to simulate it. That's fine because we are using the components we added here to simulate the inputs and outputs that we want. Okay, and we want to load our microcontroller code into the microcontroller. So we're just going to go to the microcontroller properties, and under program file, we will go and find firmware. Okay, now we could use the hex file, The COF file includes some additional information which can make the debugging easier. We can step through the source code, and it contains a list of our variables and stuff like that. So we could use the hex file, and again you can use any compiler, any IDE, as long as it generates a hex file or a COF file or any other supported file. You can bring it into Proteus and simulate it. So we'll use that COF file there. Our microcontroller is running at 48 megahertz, and we're going to leave the USB simulation off for now. I'm just going to take a quick look at our project in MPLAB X here. So again, it's a very simple project. We just have one main.c file. The peripheral libraries were generated with the microchip code configurator, and our program very simply just reads the analog input, sets the PWM output, prints the values on the USB and the UART, and sets the LEDs depending on the level of the input. Okay, so that's it. We can go ahead and run the simulation. Okay, we're going to adjust the knobs on our oscilloscope a little. Okay, and as we adjust the value on our input, you can see that the PWM is scaling as we were wanting it to. So our microcontroller code is working well. This is actually a great debugging tool, and I used this while developing the microcontroller code to debug and to get everything working nicely for the webinar. And at this stage everything is polished and working well. You can see the voltage changing as we move the potentiometer around, and we can also see the value coming out on the UART is changing. It's currently relatively low, it's 143. We'll change it up, it's going to go up to 461. We can also see that our LEDs are changing depending on the value of the input. So everything appears to be working well. If we want to take a look at the microcontroller code, you just pause the simulation. I'm going to go into the main.c file and hit a breakpoint on the line which reads the analog input, and I can let the simulation run until it hits that breakpoint. I can check the value of the variables in my code. I'm going to add some of these variables to a watch window. And just bring up my watch window. Okay, it's currently interpreting my byte variable as the ASCII value. I'm just going to change that to an unsigned integer. Okay, and if I now go and change the value on my potentiometer, and I loop around till the next time the breakpoint is hit, I should see how these values start changing. Okay, so it was 2208, and now as I step through this code, you can see how it's starting to come down. 1676, the PWM out was 322, it's now gone to 245, the percent was 53, and that's now gone down to 40. I can see the value which is being printed out on the UART and the USB. It's 323, carriage return, line feed, and null terminator. If I want to step into this routine which was generated by the microchip code configurator, you can just hit step into, and I can see exactly what it's doing. It's setting the ADCON 0 bits, sets the go done bits, and then it loops around until that go done bit is cleared. We can wait around for that, so we'll just step out. Let's hit a breakpoint here where the high LED gets set, and we'll let the simulation run. Apologies, that's the low LED. Let's do the high LED here. Okay, and we'll let the simulation run, and it's going to carry on running until that breakpoint gets hit. So obviously as I'm changing my analog value up, there the breakpoints gets hit, and I can step through the code. The first thing it's going to do is set the low LED low. The low LED is already low, so that's not going to change anything. The next thing it's going to do is to set the OK LED low. So my OK LED is now turned off. And finally it's going to set the high LED on, and then my high LED is now turned on. Okay. My watch window stays open while the simulation is running, unlike the other windows which are only visible when the simulation is paused. So I can also see how these values change as I'm changing the input here. These are the values, the variables as they are declared in my MPLab, in my XC8 project. I can set a breakpoint depending on the value of variables. So if I want to pause the simulation when the PWM percent is greater than 80, for example, I want to see exactly which line of code caused it to go greater than 80. Then I can set a watch point condition here and say suspend the simulation when this value is greater than or equal to 80. And I'm going to start scaling that value up now, and as it hits 80, I can see exactly which line of code caused that to happen, and it is of course the line of code which sets the U8 PWM percent variable. Just go ahead and remove that breakpoint condition again. Okay, and next we're going to move on to the USB simulation. So this project uses USB CDC class, that is a virtual COM port that was generated for us automatically by the microchip code configurator. The Proteus USB simulation works best with a 32-bit operating system. Because I don't have a 32-bit operating system, I have a 64-bit operating system. What I'm going to do is I'm going to interact with a 32-bit virtual machine operating system. Using a virtual machine is also useful in that if there's any problem with your USB code, which could potentially cause a crash on your computer, you're not going to crash the main computer, you're only going to crash the virtual machine. Proteus interacts with Windows at a very low level on the USB drivers. So again, the virtual machine can just help to protect against that. I haven't personally actually seen any crashes caused, but I have found that while the USB HID class I can simulate, and also the mass storage device, the MSD classes, I can simulate those fine on my 64-bit machine. The CDC class, for some reason, doesn't want to work so well, so that one works best when I run it in the VM. Okay, so this is my virtual machine here. And what I need to do is I need to get the IP address of the virtual machine. So I've gone and started a command prompt and I've run ipconfig. I've got the IP address there. So I'm going to go and enter it in Proteus. Okay, and if I go ahead and run the simulation now, I can see that Windows has picked up my CDC, my virtual COM port, and what's basically happened here is that Windows thinks that we have plugged this circuit into the computer. As far as Windows knows, this is a real USB circuit which has been plugged into it. If I stop the simulation, it's going to unplug the USB. That virtual COM port is going to disappear again. If I start the simulation again, then my virtual COM port is back. I can go and open some terminal software, connect to the virtual COM port, and I can see those values coming through. If I change the value on my input, you can see that the values coming through on the virtual COM port are also changing. I also put together a micro C project which uses a USB HID class rather than a USB CDC class. So we'll go and get that firmware quickly. And if we go ahead and run this one, you can see that it pops up under the HID devices in Device Manager. My little HID terminal program here, it's got the vendor ID and the product ID, and you can see that the device is connected and the values are coming through. Again, if I change the value on the potentiometer, then I can see how the values coming through in the HID terminal are changing. If I disconnect my USB, I can see that the unit is now disconnected. It disappears from Device Manager. If I run it again, it's now back connected again and back in Device Manager. So as I mentioned, the HID class does seem to work fine even on my 64-bit machine. We can test that quickly. There we go, the values are coming through here. And again, if I change the value on the potentiometer, then the value is coming through on my HID ready to change. There's also the USB transaction analyzer in Proteus. So I'll go and change this back to the virtual machine. See, the transaction analyzer doesn't have to work with the virtual machine. It can work normally as well. Then I can see the exact packets which are getting exchanged on the USB bus. For anyone who's a bit more familiar with USB and the lower layers of the protocol, this will probably be very interesting. I can see the exact packets that are being sent through, and I can see, for example, here's my 69 text, which I'm seeing coming through in the HID terminal. Proteus has a lot of great simulation capabilities. It's one of the things which sets it apart from a lot of other packages. This is only demonstrating some of the simulation capabilities. There's a lot of sample projects available which demonstrate some of the other capabilities. And you're also welcome to contact me for more information. Okay, so the next thing that we want to do is we want to route our USB data plus and data minus pins as a proper differential pair. So this is something to do with high-speed design, which has to do with things like signal integrity and reflections on the lines, as well as the signal travel times. Electricity doesn't travel infinitely fast, and when we're dealing with very high-speed signals, signals which are changing very, very quickly, then you have to take into consideration the amount of time that the signal actually takes to travel from the transmitter to the receiver, to make sure that where we have for example, a clock and a data line, you want the clock and data edges to be arriving at the receiver at the same time, so that we don't get a mix-up between our clock and data edges. So that's what length matching is for, and then we also need to, basically what's happening is what we were thinking of as a DC signal is now starting to move into the domain of AC and RF. So things like impedance, the AC concept of impedance, are starting to become important, very, very important on our design. Also things like EMI start coming into play. This is not a presentation on high-speed design theory as such, but suffice to say that according to the USB spec, we are supposed to route these USB data plus and data minus lines as a differential pair with 90 ohm differential impedance. We can perhaps organize a separate webinar presentation on high-speed design theory if there's demand. I know that there's some other guys in South Africa who've run some very good high-speed design courses. But for now, we're just going to look at exactly how do we route a differential pair in Proteus. And once again, this board will probably work fine as it is, just like this. If you produce this board, you most likely not see any problems with it. But certainly as you're moving into higher speeds, USB 2, USB 3, and also just for compliance and to do things according to the spec, this differential pair should have a 90 ohm differential impedance. It's not really feasible to route 90 ohm differential impedance on a 1.6 millimeter 2-layer board, simply because the tracks will have to be way too big, way too thick in order to get that impedance. So we're going to change to a 4-layer board, which is going to make things somewhat easier for us. The USB, the parameters that we need in order to reach that 90 ohm impedance, I've calculated using a tool like the Saturn PCB design toolkit, and we can see the conductor widths and spacing that we need according to certain core and prepreg thicknesses. So we're going to go ahead and change this to 4-layer board. I'm going to set the core thickness to 0.8 millimeters. And we're going to change our bottom layer to a plain layer. This is going to serve as our signal return path, so we don't want this, we want an unbroken signal return path, and we can guarantee that by changing to a plain layer and not allowing any signals on that layer. Again, these are high-speed design concepts and impedance concepts. We're going to change our inner layer 1. We're going to create a power plane on there that's connected to 3.3 volts. And on our inner 2, we're also going to create a power plane that's going to be connected to ground. Okay, and on our drill spans, we're going to say create from pause. We now have a possibility of some buried vias. And if we go to the board view, we can see our buried via possibility there. So basically what's going to happen is when the PCB manufacturer makes this PCB, if there's any buried vias, then they'll produce the core layer first, drill that, and then they'll stick the other layers on, stick the prepregs on, and do the through-hole drill thereafter. Okay, so we now have a 4-layer board. And there's 5 things that we need to do in order to set up this differential pair. So we need to add a property to each of the components which is involved in the differential pair. These curly brackets all that they do is tell Proteus to hide this value, to not display it on the schematic as such. It's kind of like ticking the hidden boxes here. So I'm just going to hit OK there, and then on the microcontroller we need the differential pairs there as well. Okay, we need to add a wire label to one of the differential pair nets, just to give the differential pair a name. Okay, and then on the PCB layout, we need to go into Design Rule Manager, and we need to create a net class for the USB, and we're going to give this the track thickness which we calculated earlier in our differential impedance calculator. Okay, and then on differential pairs, we're going to assign that USB net class to the USB differential pair. And we're going to set some parameters, again according to what we calculated, and tolerances that we are happy with. Okay, and then we're going to go onto the design rule tabs, and we're going to create two rules. We're going to create a board level rule called USB pair rule 1, and this is going to apply to the USB net class with regards to the same net class. And we're going to set the trace clearance to 12 thou, so if these tracks get any closer than that, then you'll get a DRC error. And then on the inner 2 layer, we're going to create another rule. And we're going to apply this to the USB net class, but with respect to all the other net classes. And this is just to make sure that all the other tracks keep a good clearance around our differential pair. We don't want them getting too close and messing with the impedance. Okay, and that's it. The differential pair is now set up, so now we want to actually go ahead and route it. So I'm going to route some little breakout tracks just to get down onto our inner 2 layer. And then we're going to select differential pair mode, go to our inner 2 layer, and we can go ahead and route our differential pair. So in order to get the curved track there, what I did was I held down the control key on the keyboard, and curved tracks are generally better for maintaining impedance than square or mitered tracks. Okay, and this is currently, I think I just need to redo these breakouts here. And top copper. Okay. That's better. So just do that, and there we go. So that's our differential pair routed. We can see that the squiggle has a serpentine squiggle has been added for us there if we want to see exactly what is going on with this differential pair. Let's see. Okay, so the green is where our differential pair is in phase, the red is where it's out of phase, and the brown is where it's being rephased. So basically our outer track here is a bit longer, obviously, than our inner track. So in order to get them back in sync, we need to add a little squiggle after which they are now back in sync. Okay, and that's it for the differential pair routing. Just going to take a quick look. This is obviously a very simple board, so I'm just going to take a quick look at a bit of a more heavyweight high-speed design, just to see what is possible. So this design here is a breakout board / plug-in module for a Intel Area 10 FPGA. It's got 4 gigabytes of DDR3, it's got eMMC, it's got a 16-bit ADC on board, and it's a 14-layer board. So again, just a bit of a showcase of what is possible. Okay, so the last thing we want to do is take a quick look at the project notes module. There's a number of reports in there which can help to make sure that there's no errors on the board, and it's also just a nice way of putting together a sort of an audit of the board / information for the guys doing the manufacturing and the PCB assembly. So we can go to the Project Notes tab, and the first thing we're going to do is just go to our schematic capture and add some properties to our design. Okay, and then we're going to bring these in to our report. Okay, and these values are dynamic. They will update if we do a future board revision. They'll update automatically. We'll also insert the last date of modification to the file. Okay, and then I'm going to insert that assembly plot that we looked at earlier and generated a PDF of. Okay, I'll insert a length matching report. Okay, so my length matches are currently within tolerance. If I were to go and mess with my length matches, so if I go and make this route longer than what it was, and I go and update that, I can see that my length matching is no longer valid. And I'll just go and undo that, and then my length matching is within tolerance again. I can also insert a differential pair report. Again, everything with my differential pair is still within tolerance and all good. And I can also insert something called a single pin net report. Okay, so I have a lot of listings here in my single pin net report. The purpose of the single pin net report is to try and make sure that you don't have, for example, 2 terminals on your design which you thought were connected, but you've given them slightly different names. I'll illustrate that shortly with an example. But also any component pins which are left unconnected will show up in the single pin net report. So we're just going to put a bunch of no connect pins on all of our unused pins. Okay, we're going to go and rerun our single pin net report and see most of those problems are resolved. I've hooked up these TX and RX pins, but I haven't actually hooked them up to any connect or anything. They're only hooked up to the virtual terminal, so Proteus is rightly reporting them as single pin nets, but we're going to ignore that for now unless I want to put another connector on the board to actually break those pins out. To illustrate the naming, the terminal naming scenario I mentioned earlier, let's say for example I called this terminal here LED high, HIGH, and I called this one here LED high, just HI. Perhaps a typo or mistake I made when designing the board, then the single pin net is going to pick this up for me. So that's just a helpful audit feature. If I go and change that back again, then those pins have been removed from the report. And that's it. We've completed the presentation. Thanks again to everyone for joining the webinar and for the discussions and polls on the webinar as well. Those were really interesting. And for watching this video. Again, the project files are available for download from the link in the description, or alternatively just please contact me via our website at www.dizzy.co.za, and I'll be happy to send them to you. If there's any other questions or anything else I can assist with, then you're also welcome to contact me via the aforementioned methods. Thanks again everyone for watching, and have a good day further. Cheers.